All right, so another application. We said in the previous video that in order to be able to calculate square roots, our little Newton scheme required us to be able to do a division, which is a very expensive operation to do. And so here we are going to look at a way to do division without actually dividing anything. We learned to do long division, about the time we're in third grade or fourth grade. My second grader is at home right now because everybody's at home, and he's been asking about how to do division, so I don't think they've covered that yet. Um, but we've been doing long division for quite a while, certainly since we were maybe 10 years old, and we know that it's a colossal pain in the ass to do. It's a very tricky process. It's not obvious why it works or how it works or why it's supposed to work the way that it does. It's not something that we could just do because we feel like it. I guess we could, but it's not something that we would do unless we had to. There are a lot of places that we can make mistakes, even simple small mistakes, especially early on, can radically change the quotient that we're after. So again, long division is a big problem even for humans. For computers, it's a very, very expensive operation to do. It requires, if you're doing it in hardware, it requires a lot of dedicated hardware, and the hardware is expensive. You're talking about spots on a computer chip, and every even like square millimeter is going to cost a lot of money. And this is going to be a significant amount of resources that are dedicated to just doing long division. And if we don't have to do it, we don't want to do it. So, Newton's method is going to give us a way to do that without actually ever dividing anything. We can take advantage of multiplication and addition, which are very, very easy to do, very, very fast for computers to do, whereas division, again, is a very, very costly and expensive and time-consuming process. So, we know that the solution to this equation is x equals 1 over a. So if I wanted to know what is if I want to know how to divide by 1.83, that is, I want to divide by 1.83. What we know about fractions is that this is the same as multiplying by 1 over 1.83. So that would be the solution to our equation. And if I want to divide by 1.83, I would solve 1 minus x minus 1.83 equals 0. And that will give me a decimal approximation to this quantity here. And then I could multiply by that. All right. So let's solve using Newton's method. Let's put f of x as 1 over x minus a. Then f prime of x is just negative 1 over x squared. We'll set up our Newton scheme. X sub n plus 1 equals x sub n minus f of xn over f prime of xn. That is xn minus 1 over x minus a, all divided by negative 1 over xn squared. That's xn. Two minus signs are going to make this positive. And then we need to do this division. We want to simplify that. That's 1 over xn minus a, and we want to divide that by 1 over xn squared. Well, how do we divide with fractions? We're going to change this to a multiplication, and we're going to find the reciprocal of this. So 1 over xn minus a times, now xn squared over 1. We can throw away the over 1. We know that's not going to change anything, and distribute. That gives us xn squared over xn minus a times xn squared. And xn squared over xn is just xn. We'll put the purple stuff here back into our Newton's scheme and get xn plus 1 is equal to xn excuse me, plus xn minus axn squared, or xn plus 1 is equal to 2xn minus axn squared. Notice that there is no division required in order to be able to use this formula. If we go through that formula enough times, that will give us an estimate for the, say, the decimal approximation of 1 over 1.83, and then we can multiply by that instead of dividing. So let's let A be that 1.83. Then 1 over 1.83 is probably a little bit more than 1 over 2. If we make the denominator of our fraction just a little bit smaller, we're going to make the value of the fraction just a little bit bigger, and that's 0.5. We'll take that as our initial guess. So we'll take x0 to be 0.5, and then xn plus 1 is going to be 2xn minus 1.83 times xn squared. So let's put that into our calculator. 0.5, we want to store that as our initial guess, and then calculate 2xn minus 1.83. Did I get it? No. Times xn squared. This will calculate x1. If we store that back into x, then we can calculate all of our iterates. This is the third iteration. This is x3, and we see that it is the same as x2 up to 4 decimal digits. Now we have 1, 2, 3, 4, 5, 6, 7, 8 digits that are the same, and it is only these last 2 digits that are not. And if I want this out to all 10 decimal places that my calculator is going to display, this was, 5 iterations of Newton's method. If I simply ask for 1 divided by 1.83, we see that we get exactly the same value. Only we have calculated that without needing to be able to do any division at all. We can do that exclusively through this Newton scheme, where we need to be able to multiply. We need to be able to, well, squaring is just a multiply, and this is a multiply. So 3 multiplications and 1 subtraction in order to be able to do division. We went through this process 4 times, 5 times. So that's 12 multiplications and 3 subtractions. 4 subtractions is not very much. And overall, that process is likely to, even going through all the multiplications and subtractions, is still probably going to be a lot less time consuming for a computer to do than actually going through long division. You may think this seems sort of silly. Computers are very, very fast, and it hardly took the calculator any time at all to do this. keep in mind that we are calculating one reciprocal, 1 over 1.83. We did that once. The computer, when it's solving an equation in a million variables, or even just 1,000 variables, or even just 10 variables, when it's solving equations like that, it's got to do billions of calculations. And doing billions of divisions, if I can make that take less time, is going to be a good thing. And so Newton's method gives us a very, very powerful, very fast way to come up with a reciprocal, and then we can do division by multiplying by the reciprocal. It gives us a very powerful way to come up with those reciprocals without ever actually having to do division. We'll do one more with this. We would like to find or estimate 1 over 8.32. So we'll let A be 8.32. We need to estimate 1 over 8.32 in order to get our initial guess. This is going to be pretty close probably to 1 over 8, which is 0.125. We probably could say that 1 over 8.32 is pretty close to 1 over 10, because 10 is pretty close to 8.32. And even then, 1 over 10 is just 0.1. That's a very easy thing to come up with. This scheme is not as robust as the one for square roots. Having a bad initial guess can radically change the behavior, and I'll show you that here in just a minute. But with a halfway decent initial guess, we can come up with a pretty good estimation of this reciprocal very fast. So xn plus 1 is 2xn minus 8.32 times xn squared, and we'll type that in. So 0.125, store that as x, and then 2xn minus 8.32 xn squared. We want to store that back into x. Okay. So this was 4 iterations, and already we see that we have 10 decimal places worth of accuracy. Very, very fast. Now, what if we had a bad initial guess? What if we took something like 1 over 8.32 is approximately equal to 1 over 1, which is 1. Yeah, that's a terrible, terrible estimate. But when we start going back through our Newton process, we see that we get terrible, terrible results from that. In fact, in 3 iterations or 4 iterations, Newton's method is telling us that our reciprocal is about negative 8 trillion instead of instead of 0.102 or something like that. So again, good initial guess in some cases is required to make this method work. We could probably start with 0.15 as our initial guess. And come up with the same value, so 1.202, with an initial guess of 0.15 rather than 0.125. But our initial guess of 1 was terrible and led to terrible results as a consequence. Our square root algorithm is much more robust in picking a bad initial guess than our reciprocal algorithm. So using this is going to take a little bit more care to make sure that our initial guess is good. But just a little bit of introduction to the way that we approximate all sorts of different kinds of values beyond just the linearization that we looked at the beginning, at the roughly the middle of the semester. This is called an iterative process because we repeat the same sort of calculation over and over and over again. The Newton's method in general for most problems is what's called a second order method, which means that it roughly doubles the number of correct decimal places every time you go through the iteration. Now, of course, picking our bad initial guess like we did here kind of screws that up. But picking a good initial guess and applying it in problems where Newton's method actually is going to work roughly doubles the number of correct decimal places every time you go through that calculation. So the first time you may get one decimal place, the second time two, then four, then eight, then 16. And we see that in just 5 iterations, we've already gotten more decimal digits correct than our calculator is able to display. So there are more powerful, more accurate schemes. There are numerical techniques for solving equations that are higher than first order. So third order, you would instead of doubling the number of decimal places that are correct, you might triple the number of decimal places that are correct. Instead, or a fourth order scheme, you would get 4 times as many correct decimal places every time you go through the calculation. Those tend to be considerably more costly, involve a lot more operations. So here, again, we said that we need to be able to do 1, 2, 3 multiplications and 1 subtraction. A fourth order scheme might require 20 or 30 multiplications and additions and subtractions in order to be able to come up with the estimate. But the trade-off is that you can get better solutions faster. But yeah, again, the whole sort of field of numerical analysis is there to talk about how these schemes work, why they work, what cases are they not going to work, and what we can do about it. So we will pick up with one of the last sections for the semester. We'll do next week, but this week all about Newton's method. So thank you.